good morning, ladies and gentlemen. My name is Karen Lombard. I'm a physical sciences teacher at Unisi High School in Bloemfontein. Today we'll be looking at questions on work, energy and power. This tends to be one of the trickier questions in paper 1 that you'll be writing. So I've decided, seeing as how you are the learners who are wanting to achieve top marks, that this would be a good area to have a bit of a look at. So we're going to be looking at work, energy and power. I am not going to spend very much time on the theory. I believe that you would have covered the theory up until this stage. So I'm going to spend most of my time looking at examples and how to apply the theory to the actual examples from exam papers. Now, I will be taking a number of examples from this book, right? The book that you received from the Department of Education. It's the Terms and Definitions, Questions and Answers for paper 1. I will give you page numbers when I'm working on specific examples. Please remember that the memos are also available, but always try to do a question without turning to the memo first. Right, back yourself. Trust yourself to get the answer the whole way through, and only at the end go back and look at the memo. All right, your definitions, I'm not going to go through all of them. They're in the book that I've just shown you. Please make sure that you are really, really confident with your definitions and your laws. Again, whenever we are given a definition or a principle or a law, your exam guidelines will also give you the relevant equation that needs to go with that specific section. So for example, when they define work for you, not only will they define work, but they are also going to give you the equation needed for calculating work. Same, for example, when they speak about non-conservative forces, they give you the definition of non-conservative force and then also give you the equation involved with the non-conservative force. Again, with power, there's your equation for power. So make use of these books. These definitions were taken out of the book that I've just shown you, but also obviously in your exam guidelines, all the definitions with the equations will be given to you. It is essential when you start the section on work, energy and power that you are comfortable with your grade 11 work on Newton's laws. Now, luckily, you would have written on Newton's laws in March, in the March common test. So this would already have been revised before March. So when you started this section at the beginning of the second term, luckily most of this work would have been familiar to you. We again, in this section of work, deal with frictional forces, which comes from Newton's laws. We look at applied forces. We look at calculating Fnet. So a great deal of this section of work is based on your Newton's laws. So please make sure before you tackle this section of work before the exam that you just go back and revise your grade 11 work. All right, let's just have a quick discussion about what work is. And I know that your teacher would have done similar examples with you. First of all, let's look at this man carrying a bag full of Lego. Is this man doing work on the bag? Now, first of all, remember that the wording, the terminology in this section is odd. We ask, is work being done on an object? So my question to you is the man doing work on the bag? Now, the first thing that you'll always do in answering these questions is to draw a free body diagram. Now, you all know the importance of free body diagrams in physics, especially in mechanics. So let's start off by drawing the bag. And now let's draw in the forces acting on that bag. Remember, please, to always use a ruler when you're drawing free body diagrams. All right, there are only two forces acting on this bag. The most obvious one is the downward force of weight, or the force due to gravity. And the second one is the force that the man is applying to the bag to keep it in position. And that will be an upward force, right? He's applying an upward force on that bag. Right, if we label those, that is going to be the applied force, and that is the force due to gravity or weight. So if I look at that free body diagram, that shows me all the vertical forces acting on the bag. In this case, there are no horizontal forces acting on the bag. Now, in what direction is the bag itself moving? The man is walking towards your right, which means that the bag is also moving to the right. So the displacement of the bag is to the right. Now, if I look at those vectors, displacement is a vector to the right, and the applied force of the man is a vector which is upwards, vertically upwards. Now, ask yourself the question, what is the angle between the applied force and the displacement of the bag? Right, so the applied force is vertically upwards, displacement is to the right. So the angle between those two is going to be 90 degrees. Now, if we go back to our equation for work, remember I said to you I'm not going to spend too much time on the theory. The equation for work is W is equal to F delta X cos theta. Now, what is that theta? Let me just write this a bit bigger for you. W is equal to F delta X cos theta. Now, what is that theta? What does that angle refer to? That is the angle between the displacement of the object and the applied force that is doing the work on the object. So in this case, theta is going to be 90 degrees. That's why I got you to draw your free body diagram, so you could see that relationship. Now, if you've got your calculators in front of you, which you should, in physics, you always need your calculator. Type in for me in your calculator cos of 90 degrees. And you should get an answer of 0. Now, if cos of 90 degrees is 0, it means that this entire right-hand expression in the equation is equal to 0, which means that the work done by the applied force is also going to be 0. So let's answer the question. Is the man doing work on the bag? And the answer is going to be no, because the angle between the displacement of the bag and the applied force is 90 degrees, which immediately means that no work is being done on that bag. Right. His arm might get tired. He might feel like he's doing work on that bag. But according to the equation, work is not being done on that bag. Let's look at a second example. Here we've got someone working out in the gym. And this gentleman is applying a force on those weights. He's lifting those weights upwards. And the question is, again, is the man doing work on those weights? Follow the same process as we did in the previous example. Draw a free body diagram showing the forces acting on those weights. There are my weights. What forces are acting on this object? There is always the downward force of weight, which is going to be vertically downwards. And then this man is applying an upward force on those weights. So the force, the applied force, is going to be upwards. So this is going to be the force due to gravity or weight, and this is going to be the applied force acting on those weights. Now, in what direction are those weights moving? Right, those weights are being pushed vertically upwards. So the displacement of the weights, oops, sorry, that's a very ugly line. The displacement of the weight is vertically upwards. Now again, as in the previous example, what is the angle between the applied force and the displacement of the weights? The applied force is vertically upwards. The displacement of the weight is vertically upwards, which means that the angle between the two is 0 degrees. Now again, let's look at the equation. W is equal to F delta X cos theta. What is theta? It is the angle between the displacement and the force. And in this case, it's going to be the cos of 0 degrees. Right. If you type in cos of 0 degrees, you're going to get an answer of 1, which means that work is being done on those weights. Right. Now, before we can tackle some of the more difficult examples involving work, energy, and power, we need to just be reminded again from grade 11 how to work with components of weight. Now, remember that if an object is placed on a slope, so here I've got a 5-kilogram crate or block that has been placed on an incline that makes an angle of 30 degrees to the horizontal. And the question is, which forces are doing work on this object, right? Which forces are doing work on this object? Now, I think the first thing that we need to do is to draw a proper, complete free body diagram of all the forces acting on the object. Right, if that object is stationary, right, there's my object. Let's look at all the forces acting on this object. If it is stationary, it means that there has to be a frictional force that is preventing the object from sliding down the slope. And friction will always oppose motion. So this block would like to move down the slope. So friction is opposing that motion, which means that we are going to have a frictional force. Immediately label your diagram. So that is my frictional force. What other forces are acting on the object? There's always the downward force of weight, or the force due to gravity, which is always vertically downwards. And because this object is on a slope, or it's on a surface, any object in contact with a surface will always experience a normal force. And please remember that normal forces are always perpendicular to the surface. So in this case, the normal force has to be perpendicular to the slope. So there is my normal force. Now, if you were asked in an exam to draw a free body diagram showing the forces acting on that object, that is what you would draw. It would be a 3-mark question, and you would get 1 mark for each of those forces acting on the object. But now, the question is, which forces are doing work on the object? Now you need to remember that because the object is on a slope, this force due to gravity, weight, can be broken down into 2 components. And this is work that we did in grade 11. That force can be broken down into Wx, which is the parallel component of weight, and it can be broken down into Wy. Also called the perpendicular component of weight. Now please remember, if you are asked to draw a free body diagram for marks, you never show the components. You only show the actual force, never the components. But in this question, they are asking you which forces are doing work on the object. So you need for yourself to actually break this down into the components so that you can identify all the forces acting on the object. If you have got Wx and Wy, please remember to remove weight. You cannot have weight as well as Wx and Wy in a free body diagram because Wx and y are W, right? Combined together, they give you weight or the force due to gravity. Now let's answer the question. Which forces are doing work on the object? Now, if the object was to move, the object would move down the slope, right? So the object is going to be moving down the slope. So the displacement of our object, delta x, is down the slope. So my question to you is this. Will the normal force do work on this object? Right, remember how we determined this in the previous example. What is the angle between the normal force and delta x? The angle is 90 degrees. So will the normal force do work on this object? The answer is no, because the force is perpendicular to the motion of the object. Now, name one other force for me here that is not going to do work on the object? Right? Which is the only other force that is acting perpendicular to the motion of the object? That would be Wy, which means that both our normal and Wy do not do work on the object. However, Wx and F will both do work on the object. Wx makes an angle of 0 degrees with the displacement, and the frictional force makes an angle of 180 degrees with the displacement. So both Wx and the frictional force will do work on the object. All right, a quick reminder of the different equations involved in calculating work. The first one we've already looked at. This is simply to calculate the work done by a single force on an object. So the work done by a force is equal to the force times by delta x times by cos of theta. So that one we've already looked at. The second one is Wnet is equal to delta EK. Now this one is called the work energy theorem. It is given in your exam guidelines, both the definition of the work energy theorem as well as the equation. So Wnet is equal to delta EK. The most important thing to remember here is that it is Wnet. In other words, the work done, the sum of the work done by all the forces acting on the object. So in our previous example, we had a number of forces that were doing work on the object. If I calculate the work done by Wx and friction, and I add them together, I will get the net work done by the forces. And then the third one is Wnc is equal to delta Ek plus delta Ep. That Nc, the subscript Nc, stands for non-conservative forces. Remember, we've done the theory of conservative and non-conservative forces. A conservative force is like the force due to gravity, right? All other forces, friction, applied forces, tension, would all be considered non-conservative forces. I'm not going to go through that theory again. Please just make sure that you are happy with that as a background. Please remember as well that work done can also be defined as energy transferred. In grade 11, when we did electric circuits, this is how we defined work done. Work done is the energy transferred. Please also remember that power is the rate at which work is done, or the rate at which energy is transferred. So if we look at our equations for power, power is the work done, or energy transferred, divided by time. Why divided by time? Because rate means divided by unit time. We also have a second equation for power. P average is equal to the force that's being applied times by the average velocity of the object. We often tend to forget about this equation. We get very caught up when we're calculating power in this equation here, and we forget that this is a very useful little equation that we can use. But I'm now going to do examples where we incorporate all of these different equations. All right, this is a fairly famous question that's been around for a while. It appeared in an exam quite a few years ago, and it has kind of been used as a standard example ever since then. Now, I strongly recommend that when you go into a physical sciences exam, you take highlighters with you. Now, please remember, you are not allowed to use highlighters or colored pens on your answer booklet. So when you're answering questions, you may not use highlighters or colored pens, but you may use highlighters in your question paper to allow you to differentiate between different sections of the question. All right, ladies and gentlemen, please make sure that you now fill in the relevant information that you've got. We are told that as the block reaches this point here, in other words, the beginning of the rough surface, its initial velocity is 7 meters per second. We are then told it moves those 2 meters, hits a frictionless ramp, and moves up that frictionless ramp until it comes to rest at the top of the ramp. Now, comes to rest means that its final velocity at this point is equal to 0. Right, so our final velocity there is 0. Now, the question is, show by calculation that the speed of the block at the bottom of the ramp is 3 meters per second. So in other words, they want to know what is the velocity at this point here. Right, what is the velocity at the bottom of the ramp? So in other words, they are saying it hits this section here with a velocity of 7 meters per second. What is its velocity after traveling 2 meters across that section? Now, the biggest confusion always comes in with this 3 meters per second. They are saying, show by calculation that the velocity at that point is 3 meters per second. But now the question is, may I use that value in my calculation? Right, to help you out with this, I'm going to give you a silly example. If you go to the Bloem Show or to Ratanga Junction, anywhere where there are roller coasters, very often they've got a little sign next to the entrance where it says that you have to be 1.2 meters tall in order to go on that ride. Now, if you want to know my height, you do not use that 1,2 meters in calculating my height. The 1,2 meters is a reference. If my height is greater than 1,2 meters, I may go on the ride. If I'm shorter than that, I may not go on the ride. This 3 meters per second is the reference. You want to show that the velocity at that point is 3 meters per second, but you can't use the value in your actual calculation. It is the standard to which you're going to compare your answer, right? Now, I am going to set a bit of a limit on this question. You may only use energy principles in calculating this question. So in other words, I don't want you using equations of motion or Newton's second law at all in doing this calculation. You may only use energy principles. So what are we going to do? Always start off by drawing a free body diagram. That is the first thing that you always do, is you draw a free body diagram. So as that 3 kilogram object hits onto the rough surface, let's look at what forces are acting on it. First of all, there's always going to be weight. And please use a ruler. I'm being bad here by not using a ruler. Because this object is on a surface, it will also experience a normal force. So we've got weight and we've got a normal force. Then, because the object is moving across a rough surface, it means that there's a frictional force. Now, the object is moving from left to right, which means that friction is towards the left. So let's fill friction in. And that is pretty much all that we've got here. All right, there are no other forces. Nobody is pushing the block, nobody is pulling the block. So there's no applied force. Right, so those are the forces that we are going to be looking at. Now, they are asking about velocity. When we are asked about velocity, the first thing that should come to mind when we think of work, energy, power, velocity is the work energy theorem. Because the work energy theorem speaks about kinetic energy. And kinetic energy has got to do with the velocity of an object. So let's write down the equation. From your data sheet, Wnet is equal to delta Ek, the change in kinetic energy. But what is Wnet? Wnet is the sum of the work done by all the forces acting on the object. So which forces are acting on the object? Now it's important to go back to your free body diagram. We have got the work done by friction plus the work done by weight plus the work done by the normal. And all of those together will then give you the change in kinetic energy. Right. But there's a bit of good news here. The first 2 examples I did with you, I asked you whether weight and normal do work on an object. Both the normal and the weight in this example are at 90 degrees to the displacement of the object, which means that the work done by weight is going to be 0. And the work done by the normal is going to be 0, which really simplifies your equation dramatically. Please show your 0 substitutions, though. You cannot just ignore those 0 substitutions, which means I now need to be able to calculate the work done by friction. What is the work done by friction? If we remember the equation, work is equal to force times by delta x times by the cos of theta. In this case, though, it's the work done by friction. So what is the work done by friction? It's the frictional force times by delta x times by the cos of theta. And all of that is going to be equal to delta Ek. Now, what is delta Ek? In physics, delta always means final minus initial. So kinetic energy is a half mv squared. But because it's delta, I'm going to start with final velocity. So it's going to be a half mvf squared minus a half mvi squared, my initial velocity. Right. Now we can substitute in. We are told that the frictional force is, now I've lost it, I think it's 30 newtons. Yes, it is. My frictional force is 30 newtons. times by delta x. How far did the block travel under the influence of that frictional force? It traveled 2 meters. So my delta x is going to be 2, times by the cos of theta. Now my displacement's to the right, friction is to the left, which means that theta is 180 degrees. And that's going to be equal to, sorry, I just want to get rid of this now. That's going to be equal to a half, which is 0.5, times by the mass of the object, which is, I think it's 3 kilograms. Yep. Right, times by 3 kilograms, times by the final velocity after the 2 meters. Now, that is the velocity that you are actually looking for. So that Vf squared is what you are going to be solving for. Minus 0.5 times by the mass, which is 3, times by the initial velocity. Now we go back to our diagram, and the initial velocity was 7 meters per second. So times by 7, sorry, I'm squishing up now, I'm running out of board. Don't forget to square that 7. Right. Now, if we solve for V, and please remember that when you, in your equation, you have actually got Vf squared. So when you solve for V, for Vf, please remember to square root your answer. Right, I'm going to give you, you can pause the video now, and you've got a few minutes then just to quickly solve for V. All right, for those of you who are finished, you should get an answer of 3 meters per second. Right, and hopefully you all did the maths correctly. Make sure that you check your substitution. Remember that you're going to get a negative value here because the cos of 180 is negative 1. Right, so that gives you your negative value on this side, and then your final answer is 3 meters per second. Right. Now, this question continued. It wasn't only 5.1. 5.2 says, draw a free body diagram to show all the forces acting on the block in a direction parallel to the incline while the block is sliding up the ramp. So now we need to go back to our original diagram. The block has now reached that position there at a velocity of 3 meters per second. It now starts moving up the ramp. Question 5.2 says, draw a free body diagram showing all the forces acting parallel to the incline as the block moves up that ramp. Now, the most important thing to remember here is that this is a frictionless surface. So there will be no frictional force acting on the object. Secondly, nobody is pushing the block. Nobody is pulling the block, which means that there is no applied force acting on the object. So what is the only force acting parallel to the surface? Right. And this is why we did components of weight just before doing this example. If we look at that block, weight acts directly downwards, vertically downwards. But because the object is on a slope, that weight can be divided into Wx and Wy. Wx that always acts parallel to the slope, down the slope, and Wy which always acts perpendicular to the slope. Remember that there's no friction, there is no applied force. So the only force acting parallel to the slope in this case is going to be Wx. So there is our free body diagram. Please remember, you don't have to draw in the slope when drawing your free body diagram. All right, what labels will we accept in this case? W parallel, written out, parallel is acceptable, or 2 parallel lines to represent W parallel. FG parallel, mg sine 20, or the component of weight parallel to the incline. We will also accept Wx. Right. Question 5.3. Calculate the distance that the block slides up the ramp. So now we go back to our original diagram. Always keep going back to your original diagram. And I'm going to get rid of as much of this as I can because it's now in our way. Right, so they want to know the distance d that this block now moves up the ramp. In other words, they want delta x. What is the object's displacement from the bottom of the ramp until it becomes stationary at the top of the ramp? What is delta x? What information do you have? You now have a whole lot of new information. We have just calculated that the initial velocity at the bottom of the ramp is equal to 3 meters per second. We also know the final velocity at the top is 0. We also know that there is only one force acting parallel to the slope. There are other forces acting on the object. There's the normal force, and there's W perpendicular or WY. But both of those forces act at 90 degrees to the displacement. So the work done by those two forces is going to be 0, which means that there's only one force that is actually doing work on the object. So we can now once again use Wnet is equal to delta Ek. Sorry, let me just do this. Wnet is equal to delta Ek. But which forces are acting on the object? Always draw a quick free body diagram. You're going to have Wy, Wx, and I'm too short, but that's the normal. Right, remember you're not getting marks for that, so it can be a bit sloppy. You really shouldn't use me as an example here. It's very badly drawn. All right, so which forces are acting on the object? It's the work done by Wx plus the work done by the normal plus the work done by Wy. Do you see the importance, ladies and gentlemen, of a free body diagram? Because now you can make sure that everything that's needed in Wnet is there, that you haven't missed any of your forces. And that is going to be equal to delta Ek. But good news, the work done by the normal, the work done by Wy are both equal to 0. So we are going to substitute in 0 there. The problem comes with the work done by Wx. Do we have Wx, the force Wx? We don't. But can we calculate it? Yes, we can. Right, from grade 11, hopefully you all remember this. From grade 11, if I draw a quick diagram for you, there's weight, Wy, and Wx. If I rearrange those three vectors to draw a closed diagram, in other words, I leave W and Wy as is, and I simply shift Wx down, I now have a triangle. This value here, this angle between W and Wy, is always the angle of your incline, right? This is grade 11 work. Are you starting to see the importance of revising your grade 11 work? The angle of the incline was 20 degrees. So now we can fill in 20 degrees in our triangle. So that value there is 20 degrees. Right. You know what weight is. You've been given the weight of this object as 3 kilograms. So the mass is 3 kilograms. So the weight is going to be equal to 3 times 9,8. You have got an angle. You have got this side, which happens to be the hypotenuse, because Wx and Wy are always going to be at 90 degrees to each other. So weight is the hypotenuse of a triangle. So you've got hypotenuse, you've got an angle, which means that you can calculate Wx. Now, how are we going to calculate Wx? Wx is the opposite side to the given angle. So in other words, we're going to use sine of theta. So Wx is equal to mg sine theta. Right, that is all grade 11 work, right? Revision from grade 11 work. So the x component of weight is equal to mg sine theta. So let's not lose track of what we're doing. We're wanting to calculate the work done by Wx. But to calculate the work done, we need Wx. So what is Wx? Wx is mg sine theta. But what is the work done by Wx? it will be Wx times by delta x times by the cos of theta. And this is what makes this section of work tricky. Your equations become long, and you've got two thetas. But please remember that they are not the same thetas. When you're calculating Wx, that theta is the angle of the incline. And it's the only time in this calculation that you will use that angle of the incline. This theta here is the angle between the force and the displacement. Right. And the displacement is up the slope, Wx is down the slope, which means that this theta is going to be 180 degrees. Right. The work done by the normal is 0, and the work done by Wy is 0. And that is all going to be equal to delta Ek, which is going to be a half mvf squared minus a half, running out of space again, mvi squared. I hope your planning is better than mine when you write on your page. All right, these equations are going to be long, so you do need space. All right, now I can substitute in. The mass of the object is 3 kilograms times by g, which is 9,8, times by the sine, and this theta, please remember, is the angle of the incline, which is 20 degrees. And all of that is now multiplied by the displacement, and that displacement is what you are calculating. That is the variable that you're looking for. So that is delta x times by the cos, and that theta is the angle between the applied force and the displacement. Wx is down the slope, displacement is up the slope, so it's cos of 180 degrees. Plus 0, plus 0. Now, here's some good news. What happens to the block when it reaches its highest point? It stops, which means that its velocity is 0, which means that this entire expression for the final kinetic energy is also going to be 0. So that simplifies your life quite substantially. Minus 0,5 times by the mass times by the initial velocity. Now remember that the initial velocity at the bottom of the slope was that calculated value, and it was 3. And don't forget to square your answer. All right. You can pause the video here, take 2 minutes, and solve for delta x, because that is what's being asked in the question. Right, I hope you made good use of your couple of minutes there in solving for delta x. Remember that in this case, delta x was actually called d, because d on the diagram was delta x. Right, so there is your substitution. Make sure that you substitute in your 0 values. There were 3 0 substitutions this time. Please make sure that all of them were there. Use brackets. Right, please make sure that you use brackets. And ladies and gentlemen, please make sure that you, at this point here, that you write cos theta, that you haven't immediately written cos of 180, because that is the actual expression or formula for work done. W is equal to F delta X cos theta. So do not substitute the 180 at this stage. Only substitute the 180 when you substitute your other values. Right. So hopefully you all got the answer of 1,34 meters. So as I said, ladies and gentlemen, this question has been around for a while, and it tends to be used as an example because it covers so many different aspects of work, energy, and power. Okay. All right, ladies and gentlemen, I'm now going to move to this book, all right, the paper 1, questions and answers. And I'm going to be working from page, I will tell you now, I believe it's page 22. Nope, it's page 19. Right, so I'm going to be working from page 19. Sorry, it says it there. As I said to you earlier, the memos are available, but please work through the questions with me first before paging back to the memo. Right, that's just cheating, and it takes all the fun out of actually working on a physics problem. All right, so this is on page 19. I know it says question 1 in your book. Mine says question 5 because I've taken it from the original exam that it appeared in. Right, but it is question 1 on page 19. And the question says as follows. The diagram shows a track ABC. The curved section AB is frictionless. So in other words, between A and B, friction is equal to 0. It's a frictionless surface. The rough horizontal section BC is 8 meters long. And there's that word again, rough. As soon as you see the word rough, you know that friction is going to be involved. So between B and C, you are going to have a frictional force acting on the block. An object of mass 10 kilograms is released from point A, which is 4 meters above the ground. It slides down the track and comes to rest at point C. Now, question 5.1.1, or in your case 1.1.1, state the principle of conservation of mechanical energy in words. Now, if I can give you one hint here, they are not going to ask you to state a law of principle if you're not going to use it. So they've asked you to state the principle of conservation of mechanical energy, which means that possibly in question 2, you're going to actually use that calculation. Right, so always use the theory questions as a bit of a guideline to help you to understand what is expected of you in the following questions. Right, I'm not going to do the theory with you now. You can state that from your exam guidelines. Then 5.1.2, is mechanical energy conserved as the object slides from A to C? Right, only yes or no. Now, your understanding of this is going to depend on whether or not you got your definition correct. So if you don't know your definitions, it's quite possible that you're going to get 5.1.2 incorrect. The principle of conservation of mechanical energy says that mechanical energy will be conserved as long as the object is in an isolated system. Now, what does an isolated system mean? It means that there are no external forces like friction present. So they are saying, from A to C, will mechanical energy be conserved? Now, between B and C, we know that friction exists. So immediately we know that this is not an isolated system, and therefore mechanical energy cannot be conserved at this stage. So your answer to 1.1.2 is no. 1.1.3, using energy principles only. In other words, no equations of motion, no Newton's second law. Using energy principles only, calculate the magnitude of the frictional force exerted on the object as it moves from B to C. Right, so they are asking you for the size of the frictional force as the object moves from position B to position C. Right. Now, this is a 6-mark question. As soon as you see a 6-mark question, you can be pretty sure that either it's going to be done in 2 steps, or you are going to have quite a complex calculation in 1 step. Now, they are asking about only between B and C, but we have very little information about B and C. But we do have more information about position A. Right, what do we know? We know that the object is released from point A. Now, when they say released, it means that its initial velocity was 0. So fill in the information that you've got on your diagram. At this point here, the velocity was equal to 0. Right. We also know that its height at this point was 4 meters. When it reaches point B, we do not know what its velocity is. But if we know the velocity at point B, we then have additional information about BC. So we actually need to be aiming for discovering what the velocity at point B is. Because once we've done that, we will then be able to have more information about section BC, which is where we are aiming for. What else do we know about B? At point B, the height of the object is now 0. Right, it's reached ground level. So the height is 0. Now, when you are being asked about velocities, you've been given heights, and in the previous question, they have asked you about mechanical energy. the first thing that should come to mind is the equation for the law of conservation of mechanical energy. Now, if you go to your data sheet, you are not given the equation for law of conservation of mechanical energy. But what you are given, and if you look at the work, energy, and power section of your data sheet, you're given the equation for kinetic energy and you're given the equation for potential energy. But you're not given for conservation of mechanical energy. Why not? Because it comes from the law. You should be able to state the equation from the law. So we know that the mechanical energy at position A is equal to the mechanical energy at position B. How do we know that? Because between A and B, there's no friction, which means that we are dealing with an isolated system. So between A and B, we do have an isolated system, which means that we can use conservation of mechanical energy in section A to B. But what is mechanical energy? Mechanical energy is the sum of the kinetic and potential energies. So this is going to be the initial potential energy at A plus the kinetic energy at A. And that will be equal to the potential energy at B plus the kinetic energy at B. Right. Now we can expand that equation using the data sheet. What is potential energy? Potential energy is the mass of the object times by acceleration due to gravity times by the height of the object at A. What is kinetic energy? It's a half times the mass of the object times by the initial velocity of the object at A squared. And then we can complete the second side. It's going to be mgh at B plus a half mv squared at B. And there is the law of conservation of mechanical energy put into equation form. Now we can fill in, but please keep going back in your mind. Don't lose focus of what you are actually being asked to calculate. They are asking you to calculate the frictional force between B and C. But to do so, you need the velocity at point B. Can I get the velocity using conservation of mechanical energy? Yes, I can. The mass of the object, see, I should have checked while I was there. The mass of the object is 10 kilograms. Times by G, which is 9,8, times by its original height, which is 4 meters as far as I can remember. Now, what was its initial velocity when it was released from point A? Its initial velocity was 0, which means that the whole expression for kinetic energy at point A is also going to be 0. Again, simplifies your substitution. Please show your 0 substitution. Now, that will be equal to mgh at B. Now, at position B, the height of the object is 0, which means that this entire expression is also equal to 0. Plus a half, which is 0,5, times by the mass, times by the velocity at B squared. And remember, we are looking for the velocity at position B so that we can now calculate the frictional force. If you now simplify and you solve for the velocity at B, please don't forget to square root your answer. It's one of the biggest mistakes when using kinetic energy calculations is that we forget to square root the answer. And you should end up with an answer of 8,85 meters per second. Right. Now, you've only done half of the calculation. That is not what they asked you. Go back and reread your question. Using energy principles, calculate the magnitude of the frictional force exerted on the object between B and C. So now we can ignore AB. We only used AB to enable us to calculate the velocity at point B, which we now have. Now we are only going to look at BC. When you're being asked to calculate a force or work done, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at the free body diagram, the first thing that you do is you draw a free body diagram. So if we look at of all the forces acting on the object as it moves from B to C. As always, there's weight. Sorry, I just need to refresh my memory. It's on a horizontal surface. So we also have a normal. Let's fix that. That's very ugly. Right, we have weight, we have a normal force. And then please remember, nobody's pushing the box, nobody's pulling the box. There is no applied force whatsoever. So what is the only force acting parallel to the surface? It's going to be the frictional force. And because the object is moving towards the right, the frictional force is then to the left. So we now have a frictional force. What is the work done by the normal force? You should know this one by now. It's going to be 0. What is the work done by weight? It's also going to be 0. So the only force doing work on this object is the frictional force. Right, so we can now use Wnet is equal to delta Ek. Ladies and gentlemen, please understand that there are numerous ways of doing these questions. You may also use Wnc is equal to delta Ep plus delta Ek. Right, that is also an option for this section of work. I have simply chosen to use the work energy theorem. If you go to turn to page 71 of this booklet, you will see that they give you the option to use Wnc as well. We do not have the time to do both options. Right, so I'm using only the work energy theorem in this case. All right, Wnet is going to be the work done by friction plus the work done by weight plus the work done by the normal is equal to delta Ek. But the work done by weight and the work done by the normal is going to be 0. The work done by friction will be equal to the frictional force times by delta x times by cos of theta plus 0 plus 0. And now I can expand my kinetic energy. It's going to be a half mvf squared minus a half mvi squared. Right, and now we can substitute in. Frictional force is what we are looking for. The displacement of the object, we are told that the object moves 8 meters under the influence of that frictional force. So the displacement, the delta x, is going to be 8 times by the cos of theta. Now remember that that theta is the angle between the force and the displacement. Displacement is to the right, friction is to the left, so it's the cos of 180 degrees. Right, so this is going to be 0.5 times by the mass, which is 10, times by the final velocity. And ladies and gentlemen, please remember here that your final velocity is going to be 0 because it comes to rest. So if we want to, let's save space and time, we can actually make that whole expression 0 minus a half times by the mass times by the initial velocity, and the initial velocity is the value that you've just calculated. Right, so on the right-hand side, please remember that your final velocity was 0, so your final kinetic energy is 0, where we substitute that in, and then we substitute in the values for the initial kinetic energy. We then solve for F because we are being asked to calculate the frictional force acting on the object. And if you solve for F, you should get an answer of 48.95 newtons. Please don't forget your units. Also, let's just go back and check what the question is. The question says, using energy principles, calculate the magnitude of the frictional force. Now, friction is a force, which is a vector quantity. So usually, we'd be expected to write or to give a direction after our unit. But because they've asked here for the magnitude, magnitude simply means size. So they are not interested in the direction of the frictional force, only the magnitude of the force. So ladies and gentlemen, that's the type of question that you can expect in the exam. There are a number of other options that you can look at. A very nice question that I suggest you go look at is the second part of this calculation, where they use a motor to lift the object. Now, please just remember that a motor simply gives us an applied force. There's nothing sinister or unusual about a motor. It simply creates the applied force that pulls that object up the slope. So I strongly recommend that you try the second part of that question. And then question 6 is a very similar type of question, where you again have an object on an incline, and that object is then moving down the incline. Right, again, I'm not going to do it because it's a very similar type of question. Now, I've left a final question for you to look at. Right, I'm going to ask that it appears on the video. It is a pendulum question, and this question incorporates momentum. Right, so it's one of those questions that crosses over between two different sections of work. Not only mechanical energy. Whenever you see a pendulum, you should immediately be thinking of mechanical energy. But because there's a collision at the bottom, there's also going to be momentum and conservation of momentum. So this is a question that I would like you to work through. You can maybe sit together in groups if you choose to, and work through this question. The diagram as well as the questions are given to you. Right, you can read through those questions, and then I'm also going to show the answers on the video. But I'll ask you again, please pause at this section, do the calculation, and then go and look at the memo before moving on. Ladies and gentlemen, best of luck for this question, the work, energy, power question in your exam. It is a challenging question, but you're young people who want to be challenged and you want to do well in this paper. So focus on this area, work hard, make sure that you understand the principles behind the work that we are doing. Best of luck.